Okay, in this section of notes, we are going to be dealing with radical expressions. We've worked before on rewriting radical expressions as exponential expressions, but what we're going to have in this one is we're going to have radical expressions where we can actually break them down and put them into their simplest components, and that's what we're going to be working on today. So in order to rewrite radical expressions, we must factor out groups of the same number we are taking the radical to the power of. Okay, all the ones that we're going to be dealing with here are square roots. I know typically I just say radicals because we could have a number on the outside, like a little 3 there for the cube root. But all these are going to be square roots that we're going to be dealing with here. So in order to take something out from underneath the radical symbol, since we're dealing with square roots, we have to take them out in pairs, okay? So in order to write the number on the outside, there must have been 2 of them on the inside, okay? So for instance, if I have 100, the square root of 100 here, okay, we would typically think of this as what number times itself gives us the 100, which hopefully we would think of 10. Now in these problems here, we might do factor trees where I would say, you know, what 2 numbers multiply together to give me 100, in which case I could say 10 and 10. Now, I didn't have to say 10 and 10. I could have also said 2 and 50 because those multiply together to give me 100. But I would just have to keep breaking down because remember, the goal is we get to the point where when we get to the point where we have a pair of numbers. So since I have a pair of 10s here, both of these are going to come out and I'm going to write it just one time on the outside, okay? So that means here that the square root of 100 can simplify down to be 10. Now, the only question is, will the square root get to stay behind, okay? Now, the square root symbol only stays behind if something is still left underneath it. Now, when I got the 10s, okay, I moved both of those out. There's nothing left underneath the square root. So sometimes we have what's called a perfect square where the entire thing comes out of underneath the bottom of the radical symbol, okay? Now, in the next one here, I have 36. Let's say I didn't think of 36 as a perfect square, okay? Because I could branch off here and do 6 and 6, and then I'd have a pair of 6s and I'd factor it out. Let's say instead I said, I have 2 and 18. Okay, I have 2 and 18. Now, typically, when I'm dealing with these ones, when I end up with a prime number, means it can't break down any farther, I typically like to underline it to let me know that that's one of my factors that I have here. Now, 18, it can also break down. I could do 2 times 9, which once again, I have another 2 here. And 9 breaks down to be 3 times 3. So there's 2 more factors. And sometimes I have students that like to write this out. So we could say 2 times 2 times 3 times 3. Because that was all that one, that one, that one, and that one. So basically what we're saying here is that the square root of 36 also equals this down here. And once again, in order to take it and write it on the outside, I have to have a pair of those numbers. So I have a pair of 2s, so I'll take it out to the outside. I also have a pair of 3s, I'll take it to the outside. And the only reason I'm writing it one time on the outside is because remember, you're doing a square root of 2 times 2. Okay, which that means the square root of 4, which means that we only have the 2. So we find if it's a pair underneath the radical, we can take it out from underneath that square root symbol and only write it once. Now that takes care of the 2s and the 3s, which cancels everything out underneath the radical symbol. So that just leaves me with 3 times 2, in which case 3 times 2 is 6. Okay, now, like I said, some of these we could have seen like, 10 times 10. Or in this one, I could have thought of 6 times 6, and I could have taken the pair out. Sometimes they're not as easy to discover like this one, okay? But I can still go about the same way. I try to think what number times another number gives me 196. And this one has a lot of numbers I could have used. If I can't think of any, I typically like to use 2, okay? Because that just means that 2 times basically half the number equals the whole number. So 2 times what gives me 196? That, would be 96. No, sorry. 98, my bad, okay? 2 times 98 gives me 196, okay? in which case I have a prime right there with the 2. 98, though, it can break down a little bit further because it can be 2 times 49, which once again I have a 2 right there. That's prime. And then 49 breaks down to be 7 and 7. Now, if I wanted to write this as one long radical symbol, I would have 2 times 2. So there's those ones. And then I would have times 7 times 7, which, whoops, forgot to underline them. There we go. Which are those ones. So basically I've accounted for everything here. And once again, we have 2 more pairs that we're going to rewrite on the outside. So there's our 2s. We're done with them. Now we got our 7s here. We got a pair of 7s. So we'll write this on the outside. That gets rid of them. In which case, we end up with just 7 times 2, which is 14. Okay? Now, they might try to throw letters in at us when it comes to these ones, and the question is, well, how do we deal with the letters? Well, when you have letters and you're dealing with square roots, what you can do is you want to look for even exponents, okay? So since this one has an even exponent, I can simplify this one a lot easier, okay? So basically here, what we have here, we have an even exponent, means that we're just going to take half of exponent, okay? So if I was writing this one out, I have the square root of x squared. My final answer here would just be to take the exponent 2 and divide it by 2. And if I did 2 divided by 2, I get, if I did 2 divided by 2, I get x to the power of 1, which is going to be my final answer here. Variables are typically easier because, once again, you're just basically taking half of the exponent away, okay? We're just going to be taking half of the exponent away. So if we take a look at the next one, we have the square root of x squared, y to the 4th, and z to the 8th, okay? Once again, notice that all exponents are even. So we're just going to do the same steps here when it comes to these. So if I take half of the squared on the x, I end up with x to the 1st. If I take half of the 4 on the y, I get y to the 2nd. If I take half of the 8 on the z, I get z to the 4th, which is my final answer. Okay? When it comes to the exponents, we basically take half of the exponent. Now, in these examples, they came out to where the radical symbol, the square root symbol, actually canceled all the way out. What if they don't? Like in these next cases here. These ones, they're going to have stuff that we don't have pairs of. Okay? So let's take a look at the square root of 250. If I go to break this one down, I could call this 2 and 125, in which case 2 is prime. 125, I could do 5 and 25, in which case 5 is prime. And then I have 25, which can break down to be 5 and 5, and then there's our prime numbers. We know we're done when we get to the point where all of our numbers here at the end are underlined because they're prime. So in this one here, we have the square root of 2 times 5 times 5 times 5. Okay, that took care of the 2 and the 3 5s. Now, once again, I can only take stuff out in pairs, okay? So I do have a pair of 5s right here that I can move to the outside and get rid of them. But unfortunately, I don't have another 5 to go with the one that I have. I don't have another 2 to go with the one that I have. So when I don't have another additional number to go with a 2 or a 5 here, the 2 and the 5 actually stay underneath the radical symbol, okay? So yeah, we move that pair of 5s outside, so I do have a 5 out there, but I still have a 2 and a 5 on the inside, in which case I would just go ahead and multiply them back together, and 2 times 5 on the inside gives me 10. Pardon me. And that's how we would rewrite that radical expression, okay? Now, if there's already a number on the outside like this, that doesn't change anything. We still go about the process like normal, okay? Now, in this one, we are going to split up 49, which is going to be 7 and 7, which are both primes, which means I'm going to end up with 2 to the square root of 7 times 7, and then we go about business like normal. I have a pair of 7s. I'll move it to the outside. I'm just going to end up multiplying it with that 2 here, okay? Now, the good news is the 7's on the inside of the radical symbol canceled out, which means the whole thing goes away, and I'm just left with 7 times 2, which is 14. Okay? Okay, let's take a look at the next one here. I have 6 times the square root of 27. Let's break down 27. 27 can be written as 3 times 9, in which case 3 is prime. 9 can be written as 3 times 3, in which case all of those are prime. Now that's going to leave me with 6 times the square root of 3 times 3 times 3. Once again, I can only take out pairs of numbers. So I do have a pair of 3's right here that can get moved out. But unfortunately, there's still 1 3 left behind. He just has to stay inside the square root. So that little 3 that was left over stays inside the square root. And on the outside, we want to do 3 times 6, which gives us 18. Okay? Now, the question is, what if they start throwing in the stuff with the letters, okay? What I typically will tell students to do on this one is when you have numbers and letters, do them separately, okay? So I'm going to make this first one be the square root of 121 times the square root of x to the 3. That way I can, still do my normal process that we've been doing this whole time. Then we can worry about the variables. Now, if I was on the number here, the square root of 121, the only numbers that multiply together to give me 121 are both 11, okay, which both those are prime, which means we have a pair of numbers that we can move to the outside, okay? So if I move those numbers to the outside, I would just end up with 11, okay? Now, when it came to x to the power of 3, typically, like we said in the last one, when the exponents are even, basically, we can just take half of the exponent and then everything else goes away. What if the exponents aren't even? Well, in that case, we're going to split up x to the 3 until we get an even exponent. And the easiest route to take there is just to have 2 x's multiplied together, okay? Now, I want one of these always to be 1, okay? Now, remember how when we multiply these, we add the exponents. So 1 plus what gives me 3? The only thing we get there is 1 plus 2. Now, why we're doing this is because now I have an even exponent here that I can take half of and write it on the outside. So that's what we're going to do here, okay? We're going to take half of this exponent and move it to the outside. So that means I'd end up with an x on the outside, and that would take care of that part right there. And the only thing left on the inside is just a regular old x. So when we have an odd exponent for these, we know something's going to get left behind, okay? But we want to make sure it's the smallest amount possible. And the smallest amount we can do is 1. Now, I ended up with 11 on the number part, and then x times the square root of x on the second part. This is basically a number times a letter. Let's just push them together for our final answer of 11x times the square root of x. Okay? Now on the last one here, we're going to do the same exact thing. They give me a number and a variable. How about let's just go ahead and make the first one the square root of 68, and then we'll times it by the square root of m to the power of 11. And we'll focus on one at a time. So 68 breaks down to be 2 and 34. Okay, because 2 times 34 is 68. So the 2 is prime. 34 breaks down to be 2 and 17. So the 2 is prime again. And also, the 17 is prime. So that means for this one, technically, we got 2 times 17. Now, once again, we take out pairs of numbers. So I have a pair of 2's that's going to get written on the outside here. Okay? I have a pair of 2's that's going to get written on the outside. So they'll cancel out inside. Unfortunately, that 17 doesn't have a pair, so that 17 is going to have to stay inside that square root symbol. And that's how we simplify that number. Now, once again, what's nice about the letters, the variable here, m to the square root of m to the power of 11, it's actually done the exact same way as before. So once again, we will write this as the square root of m times m. We'll let the first one be 1, and the only number that I can do 1 plus something to give me 11 is 1 plus 10. And we'll do the same thing as we did before. We're going to do half of this one right here and move them out. Now, when I do half of that to move it out, I'm going to end up with m to the power of 5. Okay, actually, hold on, give me 1 second here. I'm going to end up with m to the power of 5 on the outside. So that takes care of that part right there. Unfortunately, that m there has to stay behind, so we're going to leave it be, didn't stop working on me. We're going to leave that be an m on the inside. Okay? Now, well, the other one took another extra step here, so I'm just going to bring this down here real quick. M to the power of 5 times the square root of m. So I have to multiply these two together, and when you have numbers on the outside of the radical and inside the radical like we do here, you just multiply the outsides together, multiply the insides together. So we're going to do 2 times m to the 5th, which once again, number times a letter, just push them together. So we'll have 2 times m to the 5th. Square root of what's inside the radical will multiply together. So 17 times m, which would be number times a letter, so we'll push them together. 17 times m for our final answer. And I'll complete the notes for this section, so make sure you're working on the assignment. And as always, if you have any questions, send me an email.